discussing the mode summation method. And actually, this is something that you have seen in one way or other on Tuesday's lecture, okay? However, it's kind of renamed and rebranded because there are certain aspects of it that I would like to emphasize on today. Now, after I do that, which is more or less review of lecture on Tuesday, we will discuss how to do the forced undamped response to the degree of freedom system. What we did on Tuesday and the week before, when I was not here, was free vibration. Now, what we want to do, extend this concept of decoupling equations of motion, so that we can solve two degree of freedom system, which is under forced response, forced loading. Okay. So basically, it's an alternative explanation of what we did on Tuesday. Let me remind you that given the mother of all equations for a linear system, what we did, we found the natural frequencies. And for each of the natural frequencies, obviously we're discussing two degree of freedom system. So find omega 1 and omega 2. These are the natural frequencies of the system. And for each one of them, patiently find the mode shapes, U1 and U2. And if you take this U1 and U2 and put it in the columns of a matrix, what you get is the modal matrix. So this is the mode shape associated with omega 1, and this is the mode shape associated with omega 2. Now, we found out that if you take the mass matrix, the original mass matrix, and pre-multiply it by transpose of this matrix P, modal matrix, and post-multiply by P, you actually get a 2 by 2 diagonal matrix. Now, this M1 and M2 are not the same M1 and M2, because that's why I put a tilde on top of it, to remind you that these are not the same as M1 and M2 of the original 2 by 2 system. In fact, M1 is just the mode shape, transpose, times M, times U. U1 transpose MU. And this M2 tilde is U2 transpose M U2. These are just numbers. And these numbers are not necessarily the same as the original mass 1 and mass 2 that we have. Now, the same thing is going to happen with the stiffness matrix. The good thing is that the stiffness matrix, which may not have been diagonal, through this transformation, always becomes a diagonal matrix. And this is called, I put tildes here, so to remind you that this is not the same as K1 that you had for the original system, and this is not the same K2. These are, in fact, these values. So this is called the modal stiffness matrix associated with mode 1. I didn't mean the stiffness matrix. The modal stiffness associated with mode 1, and the modal mass associated with mode 1, and the same thing with the other one, which are associated with mode 2. Now, if you do this, in other words, you take the mother of all equation, which was mx dot, double dot, plus kx, pre-multiplied by P transpose, and post-multiplied by P because of the transformation, because of that transformation, you actually get a decoupled system of differential equations. So this is a diagonal matrix, which is given here. This is a diagonal matrix, which is given here. So actually, if you write it line by line, you're going to get two decoupled equations. The top equation has nothing to do with the second equation, and the second one has nothing to do with the top one. Essentially, these are, in fact, they are single degree of freedom systems which resulted from this transformation from the modal matrix. Now, we spent about 8 weeks on these single degree of freedom systems, and we found out that if you have an equation like that, you can actually solve it the solution is going to be just an amplitude times sine of a frequency, which is going with this equation, which is frequency 1. And then there is a phase angle. These phase angles, the phase angle and the amplitude here depend on the initial condition, and the same thing with the second equation. So these things depend on initial conditions of the problem. In other words, when you have an equation given to us, we have x at time 0 specified, so that gives you two conditions, and x dot at time 0 specified, that gives you two more equations, so you have four equations, and these four unknowns come from those four equations. Now let's write this thing in the expanded form. So we found Q1 and Q2, at least in theory we found it. It's right here and there. And to find the x, which is actually the variable that we're interested in, we have to multiply it by the matrix P. And if you do that, you can view, if you do this multiplication, you notice that it's actually this. Okay, it's actually this, because U11 times D1 times that, okay, plus U21 times this times that is going to be essentially coming from this column, multiplied by that row, and you're going to get this expression. Another way of writing this thing, another way of thinking about x bar equal to P, this is the P matrix, times Q, is to think about it in this term. Now notice that this is the mode shape associated with the first frequency, first degree of freedom, and this is the mode shape associated with the second frequency. Okay, so this whole thing we can write it like that: mode shape times the modal coordinate. This is called modal coordinate, the whole thing, which is your Q1, and second mode shape times the modal coordinate, second modal coordinate, the whole thing, Q2. So obviously the same thing is written, but here it is as a sum to make it easier. So if you have n degrees of freedom, then there will be sum from 1 to n, ui, di, etc. However, remember, these frequencies have to be calculated, and the mode shapes have to be calculated, and for anything beyond 2 by 2, even 3 by 3, it becomes kind of intractable in principle. Now, these, remember I said that they come from initial conditions, okay? And these are called modal coordinates. This whole thing is your Qi, which means Q1 and Q2, and I goes from 1 to 2, and these are called modal coordinates. These are the mode shape associated with mode I, and this is the frequency, natural frequency associated with mode I. In other words, this big box summarizes the whole thing. The total response is made of two pieces. In this case, this is a 2 degree of freedom made of two pieces. Mode shape times Q1. Now Q1 is called modal coordinate, and it depends obviously on the D1, omega 1, and phi1, and the same thing down here. Okay? This is for mode 2. That's why this is called modal summation or mode summation method. Now these DIs that you saw a minute ago here are right there, the DI here, D1 and D2 in general DI. These are called modal participation factors, and it tells you how much mode 1, because it's a multiplier of mode of that sine term basically. It tells you how much of that is actually important, is participating in the overall response. If DI is very, very small, means that that particular mode, for example, if D2 is very, very small, it means that that particular mode actually does not participate much, and therefore one can probably ignore it, okay? So anyway, these are called modal participation factors, and they represent how much of that mode is important. Now, let's do an example here. So we have, in the past, we have done a quarter model representation of a car where we actually ignored the mass of the wheel. But here, we're going to include the mass of the wheel or wheels, in this case, quarter model. And therefore, we have a situation like this is 2 degree of freedom system. So we can, this M1, this M1 is called the the unsprung mass, sprung mass, and this M2 is called unsprung mass, okay? So we can represent this thing physically or graphically like that, but effectively it represents the mass of the car and the mass of the tire or tires, okay? The same thing with these stiffnesses. This represents the stiffness of the tire, and this represents the basically stiffness that's coming from the suspension of the car. Now, we're ignoring damping here. What you want to do is to look at the modal superposition approach and find, for example, the displacement of the chassis x1 of t, displacement of x as a function of time. Now, the data that we have is given there. Okay, so let us go ahead and form the mass matrix. This is the stiffness matrix. Okay, these are things that you should be able to do after having done 2 weeks of, or two lectures actually, of a very simple, problem. This is a simple problem. And in order to find natural frequencies, you take minus, this is called the characteristic equation. You take the characteristic equation, set it equal to 0, and determinant of omega squared. We don't know what omega is. We have to find it. M plus k equal to 0. And this, in the long form, is going to look like that. And this is a quadratic equation. Actually, it's a fourth degree polynomial. However, terms appear as omega 4 and omega squared. So essentially, it's a quadratic equation. So you solve for the two frequencies, and you're going to get these things. Now, patiently, you have to go and take this first frequency and find the mode associated with it. Now, I'm not going to do that because this has been done twice in lecture 18 and lecture 19, so I will leave it to you to work it out. The second natural frequency is over here. You patiently go find a second mode shape. Okay, that goes with this frequency, obviously. Now, if you take these things and put it in the columns of this 2 by 2 matrix, you get the modal matrix. There we are. Modal matrix is a matrix that has the columns, these columns has the mode shapes associated with the problem. Now, if I multiply, if I create this product, I told you in lecture 19 that this is going to be a diagonal matrix, and you can work it out, okay? And by the way, if you take this 909 divided by 2000 and take the square root of it, you get exactly natural frequency. And the same thing here. If you take this 22.1 e to the 9 divided by this, and take the square root to get the natural frequency. That doesn't surprise you, because this business of decoupling the equation essentially reduces the system into two independent single degree of freedom system. And if you go to, for example, for the first single degree of freedom system, the mass is 2000 and the stiffness is 909. So if you take the 909 divided by 2000, take the square root, another square root of k over m, you get the frequency that we got. Now, there's something I want to show you here is that, in fact, I wrote by m tilde and k tilde like that, as if these were 0. But if you, for example, use, not the exact value for the modal shape, modal coordinates, these things, mode shapes. For example, 0911, etc., 4 digits after the decimal point, you're going to get something like that. If you take 7 digits after the decimal point, the numbers are some numbers are going to look different, because notice that these two are the same, and these two are the same, and the same thing with the stiffnesses, 909 and 909. And this and that are the same. But these off-diagonal terms are different. So you might say, wait a minute, this is very insensitive. So it depends how many decimals I take. That is true. However, remember, for all practical purposes, this number is 0 compared to the off-diagonal terms. Or this number is 0 compared to the off-diagonal term. So yes, the number of digits affect this. However, for all practical purposes, these off-diagonal terms are 0. This is why I literally replaced them with 0 up there. Okay. Now, remember, to solve the problem, you were given initial conditions. If you go back to the slide, I think it was slide 7 or 6, it tells you that solve the problem under these initial conditions. In other words, x of 0 is given to you, x dot of 0 is given to you. Now, since I'm solving equation in terms of q's, okay, I need q at 0 and q dot at 0, but that's very simple because it all comes from this transformation. In other words, if you wrote this thing as q equal to p inverse of x, and you plug in t equal to 0 on both sides, you're going to get q of 0. And if you differentiate this thing and plug in t equal to 0, you get this. In other words, based on my matrix P, I took only 4 digits here for convenience. The inverse of that is given there, and if you multiply P inverse by these initial conditions that were given, now I've not written it here, but x of 0 is given, x dot of 0 is given, x dot of 0, I believe it was 0 itself. Right there, x dot of 0 is 0. So you're going to get initial conditions that you want to solve the problem, q of 0 and q dot of 0. So you have 2 decoupled first single degree of freedom system with initial condition. If you look at the top line, equation, initial conditions, this is the kind of thing that we did back in week 2, okay? Or week 2, yeah, we did in week 2. Single degree of freedom system with a 0 right outside. In other words, free vibration, undamped free vibration, subject to initial condition, we did it. And this is a template from back then. In other words, if you go back to the week 2, you see that these things popped up there. In other words, the solution actually can be worked out. Now, here I have an A, or at least back then, we had an A and phi, but of course here, this is not A, this is D in general, or D1 and Phi1 and D2 and Phi2. So it's the same thing. So let's go ahead. So if you use this template from week 2, then these are the information. Plug it in. You're going to get that. Okay. Now remember, this means 10 to the minus 5. By the way, it's not negative 5. It's not e minus 5. It's 2.277 e to the minus 5, which means 10 to the minus 5. Yeah. So you're going to get this, and if you want the actual physical coordinate, you have to multiply q by p. So we got the q's right there, multiplied by the matrix P, modal matrix, and we're going to get our solution for x1 and x2, the displacement of the chassis of the car and the displacement of the wheel. And they're not the same, you can see that. Incidentally, because the phase angle is pi over 2 for both cases, where was it here? For both cases, yeah, right there, I have replaced sine of this plus pi over 2 with cosine of it. And the plot of x1, the chassis of the car, as a function of time is given here. Now remember, these things are millimeters, right? These are millimeters. Okay, good. So one last thing before we move on to the rest of the presentation. Let me write this thing look at it a different way, although this is exactly what I did for you in the previous slide, but you can also view this thing as this column times Q1 plus the second column times Q2. And that's where we can see that this is exactly what we called mode summation method. Mode summation method. Mode 1. Mode 2. Okay? All right. So we're now going to look at the case where the right-hand side is not 0. So let me take a quick break here. Okay, so the undamped system, we're still looking at the undamped situation of a 2 degree of freedom system, in general, multi-degree of freedom system, which is under a force loading, is given by this equation, which I keep referring to as the mother of all equations, okay? Now, if you write this thing for the 2 by 2 matrices, mass matrix looking like this, now remember, stiffness matrix like so, and the force vector as a vector of 2 components. Before I move any further, I want to remind you that all the mass matrices that we have used in the last 2 weeks after we started multi-degree of freedom system were diagonal. So I assume that my mass matrices are diagonal. That may not be the case depending on the choice of the coordinate x1 and x2 that you have. However, you will see that irrespective of that, when you use modal coordinates, in other words, we do that transformation going from x to p, then the resulting mass matrix and stiffness matrix will both be diagonal. But as it is, the mass matrix is as it is, the mass matrix is diagonal to begin with, and that's because of the way we have handled the course so far in this course. Okay, now so this is the long version of that. This is the long version of what you see on the top. Now, through this modal matrix, in other words, after you find the natural frequencies, the 2 natural frequencies and the 2 mode shapes associated with them, if you take those mode shapes and you put them in the column of the matrix P, you get the modal matrix. Okay. Now, we get rid of X through this change of variable, and we pre-multiply by B transpose. We know what's going to happen. We're going to get this, which is going to be diagonal matrix, and that, which is also going to be diagonal matrix. So we call that thing M tilde, and we call this thing K tilde. These are different from the M and K. It's something that you have to work out. And the right-hand side is no longer this F. It is P transpose of F. So just be aware of the fact that this right-hand side is also different from the original system. Okay, so that's what you've got. However, as I pointed out, the whole idea behind this change of coordinates is that mass matrix becomes diagonal, stiffness matrix becomes diagonal, and the right-hand side, of course, is the right-hand side. I want to remind you what this M1 tilde was. It was U1 transpose MU1, etc. This is the stuff that we did on Tuesday's lecture 19. Okay. Now, also as a point of reference, notice that this vector, which was obtained by taking the original vector and pre-multiplied by P transpose, can be written like so. The first column of the P matrix dotted with the original F vector, and the second column of the P matrix, modal matrix, dotted with the original F vector, force vector. You can write it like that, or if you don't like this dot, you can write it as U1 transpose FT, and U2 transpose FT. So it's just a matter of taste, whether you want to use the dot or whether you want to use look at it as the multiplication on the left by the transpose of the first column, etc. Now, let's move on. So notice that these are 2 independent single degree of freedom system where decoupled from each other, where the right-hand side is no longer 0, it's a function of time, and we have done this thing in the week 3 of the course. Let's do an example here. So suppose we have a beam like that, which is simply supported at 2n, and on it there is perhaps a fan or a compressor which is turning at a given RPM. It has a certain, it obviously exerts because of the inherent unbalanced, it applies a sinusoidal load to the mass M1. Okay, and mass M1 is, think about it as a fan, or the fan plus the mass of the beam in, we know how to do problems like this in from the first 3 or 4 weeks of the course. Okay, now attached to the bottom is another mass, and that is through a spring. Now stuff like this is has a very practical use, and this is called a vibration absorber. So instead of potentially this beam or that motor to oscillate up and down widely, if it was without any attachment, what we do is we make it a 2 degree of freedom system by adding a spring and a mass here. This mass is usually much smaller than that, so that instead of this guy, the motor running or the motor oscillating violently because of perhaps the speed of the fan being close to the natural frequency of the beam, what happens is that it's this mass absorbs that energy and starts vibrating very violently as opposed to the actual structure. Okay, we will talk about this thing next Thursday in lecture, that will be lecture I believe 22, where we talk about vibration absorbers. This is the data that we're going to be using, and this data is precisely what I did in the earlier earlier example. Remember the car, etc. It had, if I'm not mistaken, it had these numbers, because I'm too lazy. I don't want to go and find the natural frequencies and the modes and things like that for a whole whack of new numbers. Okay, so this kind of a thing is actually used in a very practical way. Here is a skyscraper in Taipei. This is actual 70, 80 story building tall, stories high, and on the very top there is a mast that's dangling for 3 or 4 floors. The whole idea is that if there is an earthquake and the beam, the building tries to vibrate, oscillate back and forth violently, or oscillate, it's this mass that will do the oscillation for it. So this is a vibration absorber. And here is the scale. You can see that 2 people, and there is that big blob of mass that's hanging there. So it is very common. Now here is the stuff that we did. These are the same numbers, as I said, that we used in the earlier example with the quarter model of the car. And this is the load which is being applied to the mass 1. That's why the second component is 0. And this is the driving frequency. Omega is the driving frequency, which I believe is 1. We found the natural frequency, first natural frequency and the first mode, second natural frequency and the second mode. Put it in the matrix P to get the modal matrix. And if you do this multiplication, P transpose MP, it will be diagonal, right there. And P transpose KP is also diagonal. Remember, M is called the modal mass matrix, and this K is called the modal stiffness matrix. The original M and P, these are not modal, these are not called modal, it's mass matrix, stiffness matrix. Now, once again, I remind you what I told you before. If you take the square root of K over M, you get the first natural frequency. If you take the square root of this K over this M, because this is for the second equation, you get the second natural frequency. Now, as far as the F tilde is concerned, well, we have no choice. We just have to pre-multiply it by P transpose and see what we get. So if you take this matrix, transpose it, and multiply it by that F, you're going to get exactly what you see over there. And this is a template from week three of the course. So it really tells you what the solution to the equation is when the right-hand side is not 0. See, the right-hand side is not 0, well, but it is the forcing term that's given to you here. Something like that. So this is from lecture 9. Now, we're going to use these. You have to know this stuff. You have to know everything about single degree of freedom system for the final exam. You know that. And we're going to, as you can see, we need it to do multi-degree of freedom system if we do this decoupling approach. Now, what I have here is the template for you. So if you look at, this is the template from that lecture 9. This is the steady state response. X is that, the amplitude is this, the amplitude of the vibration of that single degree of freedom system is this. There's no damping, there is 0, okay? And yeah, so for our problem, first mode, first equation was all decoupled from the second equation. So this is what we got. We have Q1, we have M1 tilde, K1 tilde, right-hand side, whatever it happens to be. In this particular problem, it came out to be 100 cosine of omega t. And there is your amplitude. Now I call this thing Q instead of X because we're going into the, we're using the Q's instead of the X's. Instead of X1, X2, we're using Q1 and Q2. That's why I call the amplitude instead of X this. And just literally write it down. So for our particular problem, this is for the template. This is for the notation that we have here. Ours can be Q1 or it can be Q2. Here is for Q1. And we wrote these coefficients. We know exactly what these things are. We just work it out. There's the solution. Q1. And for this is for the second mode, second equation, decoupled completely from the one above it, which is the first equation, and just plug in these are the coefficients, plug in the numbers, and you're going to get the solution right there. Now, I also want to remind you that the amplitude of a single degree of freedom system under a sinusoidal load, which is exactly what we have here, shoots to infinity in the absence of damping. So if you look at Q1, it's exactly a single degree of freedom system under a sinusoidal load without any damping. That's why it shoots to infinity at this natural frequency for mode 1. And the same thing happened for mode 2. That's why we have amplitude of mode 2 at the second natural frequency, which is 14 point something. This is pointing to that, pointing to that peak, okay? This 14 point something is a little bit to the left of 15. I've drawn it a lot more to the left of 15 because I wanted to, otherwise you won't be able to see it. And once again, the solution came out to be like that, and it's plotted. X1 of t is plotted, X2 of t is plotted, and this is all no damping, so it goes vibrate up and down in a sinusoidal manner without losing the amplitude. Now, before we stop this lecture, there's a couple of things I want to tell you. 2 degrees of freedom system that we have done, they don't always have to be translation. I mean, we have, for convenience, the problem that we have done were 2 masses translating. But here is a situation, for example, where we have a cart here, which is translating back and forth, vibrating back and forth, and the ball on it rolls up and down. Okay, let's say that, you see, in general, if there is no slipping involved here, these two are related, right? But in general, they don't have to be that condition. Now, here's another situation. This also is a 2 degree of freedom system because this mass can vibrate in X direction and Y direction, or X1 and X2. So this is a 2 degree of freedom system, but we're not looking for 2 masses, because as I said, most of the problem that we have done, we have 2 masses and stuff like that. Or here is the situation where these 2 are vibrating back and forth, okay? And it's a rotational motion, and these are degrees of freedom theta 1 and theta 2. Or a block which is going horizontally, vibrating horizontally, attached to it is the pendulum, which actually can swing up and down. So these are not related, okay? This displacement x and theta, they are not related. If they're not related, means that you know, there's a slip there. Okay, so now here's a situation for an airfoil. This is the example that we did in lecture 19. You may want to go back to it. This is a bounce and pitch model of a car. So let's do a quick review here. The mother of all two degree of freedom systems is linear system is this. If there is no right-hand side, there is no forcing function. Okay, and to get the natural frequencies, this is what you need to do. This is called the characteristic equation. And what we do is once we find the natural frequencies and the mode, in the case of 2 DOF, two frequencies and two mode, you put in the modal matrix and do this change of variable, and you get the mother of all equation where the equations have been decoupled. Okay, no damping. You can see that. And basically we have two single degree of freedom system and everything that goes with it in the first, I don't know, 10 weeks of the course, 9 weeks of the course. You have to know that.